You know that feeling when you're staring up at the night sky? All those stars scattered across the darkness, and between them, just nothing. Empty space, silence, vast, endless stretches where absolutely nothing seems to be happening. Or maybe you've sat in a perfectly quiet room and felt it. That sense of emptiness, like the air itself has gone still. Space feels like a backdrop, doesn't it? A blank, dark canvas where the universe just happens to place its stars and planets and galaxies. It's such an obvious thing that we barely even think about it. Empty space is, well, empty, right? But here's where things get interesting. Physics has this frustrating habit of taking the most obvious things and quietly proving them completely wrong. Over the past century, scientists have discovered something genuinely strange. Those empty regions of space, they're not empty, not even close. Energy persists where no particles exist. Subtle activity continues in places where nothing should be there. And nothing, that simple concept we all think we understand, turns out to be one of the most bizarre and complicated problems physics has ever faced. So tonight, we're asking a deceptively simple question. Is empty space really empty? Because the answer is going to change how you see everything around you. If you've ever stared up at a star-filled sky and felt small, or sat in perfect silence and wondered what fills the gaps between sounds, this video's for you. Go ahead and hit that like button and subscribe, and also let me know in the comment section where you are watching from. I read every single comment. Let's begin. An empty glass is one without water. An empty room is one without people. An empty street late at night is one where movement has paused, sound has softened, and attention drifts. In everyday life, emptiness usually means absence. Something that could be there is not there. Something that was there has gone. This way of thinking feels so natural that it barely registers as a definition at all. Emptiness appears obvious, intuitive, almost self-explanatory. It is what remains when objects are removed. It is the space left behind when matter, sound, or activity withdraws. In ordinary language, empty means clear, vacant, unused, hollow, or blank. And for most practical purposes, that definition works extremely well. But even here, something subtle is already happening. When something is described as empty, and it is rarely meant in an absolute sense, an empty glass is still full of air. An empty room is filled with light, warmth, and pressure. Even silence carries faint vibrations. Everyday emptiness is never total. It is always emptiness relative to expectation. This is where language quietly shapes intuition. Words like nothing, nowhere, and empty suggest absolute absence. They imply a kind of perfect void, a condition where there is truly nothing at all, no substance, no activity, no influence. But in practice, language is forgiving. It allows these words to be used loosely without demanding precision. Science, on the other hand, is not so relaxed. When physics asks whether something is empty, it is not asking whether something looks empty or feels empty. It is asking a much narrower and more demanding question. Empty of what exactly? Empty of matter, empty of particles equals empty of energy, empty of forces, empty of structure. Each of these is a different claim, and each requires a different kind of evidence. This is why emptiness becomes a scientific problem rather than a philosophical one. Philosophy may ask what nothingness means. Physics asks whether a region of space contains measurable properties or produces measurable effects. If it does, then it is not empty in the way physics defines emptiness, no matter how empty it appears to the senses. In classical physics, this distinction seemed manageable. Matter was made of particles. Energy was associated with motion, heat, or radiation. Forces acted through space, but space itself was treated as a passive stage. Remove the particles and what remained appeared to be nothing of consequence. A background, a container, and a silent arena where events unfolded but which did not itself participate. This view aligned neatly with everyday experience. If all objects are removed from a room, the room appears empty. If air is pumped out of a container, it is called a vacuum. The less matter present, the emptier the space appears to be. For a long time, physics followed this intuition without serious resistance. But even early on, careful thinkers noticed that emptiness was more complicated than it first appeared. Take air, for example. For much of human history, air was not considered a substance at all. It was invisible, weightless to the senses, and seemingly insubstantial. Only through experiments in the 17th century did scientists like Evangelista Torricelli and Blaise Pascal demonstrate that air has weight, pressure, and physical presence. But what had once been treated as nothing turned out to be something measurable. This pattern repeats throughout the history of science. Each time emptiness is examined more closely, new layers of structure are revealed. Things once dismissed as absence become reclassified as subtle forms of presence. This does not happen because scientists enjoy complicating simple ideas. It happens because nature refuses to cooperate with intuition. At its core, the scientific question of emptiness is a physical claim. It is a claim about what exists in a region of space and what does not. It is not enough to say that nothing can be seen there. Vision is limited. Instruments extend perception far beyond the senses, and they often detect activity where the eye sees none. If a region of space can exert a force, store energy, or transmit motion or influence matter elsewhere, then physics must treat it as something rather than nothing. This is why defining emptiness is the first scientific problem, not the last. Before any measurement can be interpreted, before any experiment can be designed, there must be clarity about what absence actually means. Otherwise, discoveries risk being misunderstood or dismissed simply because they do not fit the initial assumption of nothingness. Consider temperature as an example. Absolute zero is defined as the lowest possible temperature where thermal motion reaches its minimum. It is not defined by intuition but by precise physical limits. Similarly, emptiness requires definition in terms of physical quantities. What is the lowest possible energy state of space? But what is the minimum level of activity allowed by the laws of physics? These are not questions of language but of measurement and theory. There is also a psychological comfort in emptiness. It provides contrast. Objects feel more real when set against empty space. Motion feels meaningful when surrounded by stillness. The mind uses emptiness as a framing device. This makes it tempting to treat empty space as a neutral background, a passive absence that can be safely ignored. Physics does not grant that luxury. As understanding deepens, space itself begins to show properties. It resists compression, it bends, it stores energy, it fluctuates. None of this is obvious at human scales, and none of it announces itself loudly. But subtle does not mean insignificant. The challenge then is not to abandon intuition, but to refine it. An everyday emptiness is a useful starting point, but it cannot be the final word. Science must replace vague absence with precise definitions. Empty of particles is not the same as empty of fields. Empty of matter is not the same as empty of energy. And empty in one theory may not be empty in another. By slowing down and being careful with definitions, a deeper picture begins to form. Emptiness is no longer a single idea, but a spectrum of conditions. Some regions are emptier than others. Some forms of emptiness are achievable. Others are forbidden by the laws of nature themselves. Once definitions are clear, evidence can be allowed to speak without confusion. Measurements can be trusted to mean what they say, and the quiet assumption that nothing means nothing begins to loosen. Not through speculation or drama, but through careful, patient observation. Emptiness, it turns out, is not a destination reached after everything else is removed. It is a starting point. A question asked before understanding can move forward. And the moment that question is taken seriously, the idea of nothing becomes one of the most interesting problems physics has ever encountered. For most of human history, the idea of absolute emptiness felt not just unlikely, but deeply uncomfortable. The notion that there could be a place where nothing exists at all challenged intuition, logic, and belief all at once. Nature, as early thinkers understood it, seemed full by default. Motion happened because something pushed something else. Change occurred because substances interacted. To imagine a region with no substance, no resistance, and no cause felt less like science and more like contradiction. But this discomfort did not arise from ignorance or superstition. It grew from a sincere attempt to make sense of the world using careful reasoning. Early natural philosophy was not careless. It was systematic, structured, and deeply invested in coherence. And within that framework, emptiness appeared to cause more problems than it solved. One of the most influential voices shaping this view was Aristotle. Writing in the 4th century before the Common Era, Aristotle argued forcefully against the possibility of a vacuum. His reasoning was not casual opinion. It was grounded in a broader system of thought about motion, causation, and the nature of matter itself. According to Aristotle, motion required a medium. Objects moved through something, not through nothing. If a vacuum existed, he reasoned, motion would become undefined, and objects would accelerate infinitely because there would be no resistance to limit their speed. This was not merely unlikely, it was logically unacceptable. Nature in Aristotle's view did nothing without reason, and infinite speeds had no place in a rational universe. This led to a principle often summarized as horror vacui. While the phrase itself was coined later, the sentiment traces directly back to Aristotle's arguments. Emptiness was treated not as a neutral absence, but as a violation of natural order. Wherever space appeared empty, something must be filling it, even if it could not yet be identified. Aristotle's influence cannot be overstated. His work shaped scientific thought for nearly 2,000 years. Through the medieval period, his ideas were preserved, expanded, and integrated into broader belief systems across Europe and the Islamic world. Natural philosophy, theology, and logic became intertwined. Within this framework, questioning the impossibility of emptiness was not simply a scientific disagreement. It was a challenge to a world view. This is where belief systems began to constrain scientific questions. If the structure of the universe was assumed to be complete, purposeful, and continuous, then emptiness had no place to exist. Asking whether nothing could exist was treated less as an experiment to be performed and more as a category error. The question itself was considered misguided. As a result, many early discussions of emptiness focused on why it could not exist rather than how it might be tested. Arguments were built on logical consistency rather than measurement. The nature was expected to behave in ways that aligned with philosophical necessity. Evidence, when it appeared to conflict, was often reinterpreted rather than accepted at face value. There was also a practical limitation. Even if someone had suspected that emptiness might be possible, there was no reliable way to create it. Air was invisible and poorly understood. It was not yet recognized as a material substance with weight and pressure. Removing air from a container did not seem meaningfully different from sealing it. Without tools to manipulate pressure, emptiness remained an abstract idea. This combination of philosophical commitment and technical limitation kept emptiness at arm's length. Nature was assumed to be full because it had to be full. Any apparent gaps were treated as illusions or misunderstandings. That the universe was imagined as a continuous fabric of matter, influence, and purpose with no holes allowed. There is a certain gentle irony in this resistance. The fear of nothing was not fear in an emotional sense, but in a logical one. Emptiness threatened to unravel carefully constructed explanations. It introduced instability into systems built on balance and continuity. Rejecting the vacuum was a way of preserving order. And in fairness, the rejection worked remarkably well for a long time. Aristotle's physics explained everyday motion tolerably well. Objects fell, flames rose, heavy things behaved differently from light things. Within the scale of ordinary human experience, emptiness was not required to make sense of the world, but cracks began to form as attention turned toward more careful observation. Water pumps failed to lift water beyond certain heights. Suction behaved strangely. Pressure effects appeared where none were expected. These were not philosophical problems, they were practical ones. And practical problems have a habit of forcing new questions. Still, it took courage to ask those questions. Challenging the impossibility of emptiness meant challenging centuries of accepted wisdom. It required treating nothing not as an error, but as a hypothesis. That shift did not happen overnight, and it did not happen easily. What finally loosened the grip of this historical discomfort was not a sudden change of mind, but a slow accumulation of anomalies, situations where existing explanations strained or failed, moments when nature behaved in ways that could not be reconciled with the assumption of fullness. Once that happened, her emptiness could be approached not as a forbidden idea, but as an experimental target, something to probe, something to test, something to create, even imperfectly. The fear of nothing began to soften, replaced by curiosity about what would happen if the assumptions were wrong. The rejection of emptiness, then, was not a mistake in the usual sense. It was a reasonable conclusion drawn from limited tools and a commitment to coherence. But as tools improved and observation sharpened, the universe quietly signaled that it was ready to be questioned in new ways. And when emptiness finally became something that could be tested rather than argued, the idea of nothing began its transformation from impossibility to one of the most productive questions in science. For a long time, air and space were treated as the same thing. Both were invisible, and both offered little resistance to movement. Both seemed to exist simply as the background in which objects lived and moved. If a container looked empty, it was assumed to contain nothing of importance. The idea that air itself might be a substance took time to settle, and until it did, emptiness remained poorly defined. The shift began not with grand theory, but with stubborn practical problems. One of the most important came from something as ordinary as lifting water. In the early 17th century, engineers noticed a strange limitation. Suction pumps used widely in mines and wells could lift water only to a certain height. No matter how powerful the pump or how carefully it was constructed, the water column would rise and then stop, leaving an empty-looking space above it. This failure was puzzling. If suction worked by pulling water upward, then stronger suction should lift it higher. Yet it never did. The limit was consistent, hovering around 10 meters. For decades, this was treated as a mechanical flaw or an inconvenience rather than a clue. But eventually someone decided to look more closely. That someone was Evangelista Torricelli, a student of Galileo Galilei. In the early 1640s, Torricelli proposed a radical idea. Perhaps water was not being pulled up at all, perhaps it was being pushed, specifically pushed by the weight of the air above it. To test this, Torricelli replaced water with mercury, a much denser liquid. Mercury is roughly 13 times denser than water, which meant that if air pressure was responsible, the column should be much shorter. When Torricelli inverted a mercury-filled glass tube into a basin, the mercury fell, leaving an empty-looking space at the top. The remaining column stabilized at a height of about 76 centimeters. The result was striking. Not only did it support the idea of atmospheric pressure, it created something new and unsettling. The space above the mercury appeared to contain nothing at all. No air rushed in, no visible substance filled the gap. Torricelli called it a vacuum. This was not emptiness in a philosophical sense. It was emptiness created deliberately inside a piece of glass under controlled conditions. For the first time, emptiness could be pointed to, measured around, and discussed without abstraction. Blaise Pascal took this idea further. If air pressure was responsible for supporting the mercury column, then pressure should decrease with altitude. Pascal arranged for Torricelli's experiment to be repeated at different heights, and including the top of a mountain in France. As predicted, the mercury column was shorter at higher elevations where there was less air above pushing down. These experiments did something subtle but profound. They separated the idea of air from the idea of space. Air was no longer an invisible nothing. It had weight. It exerted pressure. It behaved like a material or substance. And if air could be removed, then emptiness was no longer just a word. It was a condition that could be created, even if imperfectly. At the same time, these experiments revealed the limits of what had been achieved. Removing air did not create absolute nothingness. The so-called vacuum above the mercury was not empty in every sense. It was empty of air, but not empty of influence. Light still passed through it, heat still transferred across it. And whatever occupied that space did not behave like a complete absence. Early vacuum chambers faced similar limitations. Air pumps improved gradually, but none could remove everything. Trace gases remained. Vapor clung to surfaces. Materials released particles slowly over time. Even the best vacuums of the 17th century were only partial. This distinction matters. An empty of air space is not the same as an empty of everything space. The experiments of Torricelli and Pascal did not prove that true emptiness existed. What they proved was something more modest and more useful. Air is not the same thing as space, and removing air does not remove all physical effects. That realization reshaped scientific thinking. If air could exert pressure, then it was a substance. If it could be removed, then emptiness was at least partially achievable. And if emptiness could be created, then it could be studied. There was also an important psychological shift. Once air became something measurable, it lost its status as a placeholder for nothing. It became one more component of the physical world, subject to laws and limits. This freed space itself to be reconsidered. If air was not space, then space might exist independently of whatever filled it. Still, the early vacuums were fragile and imperfect. They depended on glass quality, sealing techniques, and manual pumps. They could not maintain their emptiness indefinitely. Over time, air leaked back in, orifices released trapped gases, the vacuum degraded. This imperfection kept expectations in check. No one seriously claimed that true nothingness had been achieved. Instead, and the experiments highlighted how stubbornly something seemed to persist. Remove one substance and another effect remained. Clear away air and pressure vanished, but light and gravity did not. Emptiness revealed itself not as a final state but as a layered one. There is a quiet humour in this stage of discovery. Scientists set out to create nothing only to discover how many different things had to be removed before nothing could even be approximated. Each success revealed another background influence that had previously gone unnoticed. What mattered most was not the degree of emptiness achieved, but the method. Emptiness was no longer dismissed on logical grounds alone. It had become something that could be approached experimentally. This marked a turning point. Questions that had once been philosophical became physical, and claims about nothingness could now be tested rather than debated. By separating air from space, early experimenters opened a conceptual gap. A space could be empty of one thing while still containing others. Emptiness became relative, conditional, and precise. This gap would widen with time, eventually allowing physicists to ask much deeper questions about what remains when matter, energy, and even fields are stripped away. The space above Torricelli's Mercury column did not answer those questions, but it made them possible. Once air was understood as a substance rather than an invisible nothing, a new picture of the universe began to settle into place. Space itself could now be imagined as something distinct from whatever happened to fill it. This separation allowed one of the most influential ideas in physics to take shape, the idea of absolute space. With air now recognized as a substance with weight and pressure, a quiet but profound reordering of thought began to unfold. The idea that space might exist independently of what filled it was no longer a philosophical abstraction. It had been made tangible, however imperfectly, in a glass tube. But if space was not simply air, then what was it? What remained when air was removed, when light passed through, when heat transferred across an apparent void? The vacuum above the Mercury column was a physical fact, but its meaning was still uncertain. It was not nothing in the absolute sense. Something was still there, even if that something was not a substance in the usual way. This ambiguity forced a deeper question. Could space itself have properties, or was it merely a passive stage waiting for actors to enter? For a long time, the answer seemed to lean toward passivity. The success of removing air and creating a vacuum, however partial, suggested that space could indeed be cleared of tangible things, and if space could be cleared, then perhaps it was just a container, a neutral, featureless backdrop. This view reached its clearest and most influential expression in the work of Isaac Newton. In the late 17th century, Newton formulated a system of mechanics that described the motion of objects with unprecedented mathematical precision. Central to this system was a specific conception of space and time. Newton proposed that space was absolute, real, fixed, and independent. It existed whether anything occupied it or not. It did not depend on objects' motion or observation. It simply was. In Newton's framework, space was not a substance like air or water, and it had no texture, no resistance, and no ability to act. Instead, it functioned as a kind of universal reference frame, a perfectly still background against which all motion could be measured absolutely. Objects moved through space. Forces acted within it. But space itself remained unaffected. This idea solved many problems at once. Motion, for example, could now be defined clearly. An object was moving not merely relative to other objects, but relative to space itself. Acceleration became meaningful even in isolation. One of Newton's famous thought experiments involved a spinning bucket of water. Even if the bucket were alone in an otherwise empty universe, the water would climb up the sides as it spun, revealing that the rotation was real. The curved surface of the water indicated motion relative to absolute space. That's not merely relative to the bucket's walls. Within this system, emptiness worked beautifully as a passive stage. Remove all matter from a region and nothing essential changed. Forces still acted according to their laws. Objects entering the region behaved exactly as expected. Space did not interfere, respond, or participate. It simply allowed events to unfold. Classical mechanics relied deeply on this assumption. Newton's laws of motion described how objects behaved under forces, but they said nothing about space itself, changing or reacting. Space provided positions, distances, and directions. Time provided duration. Together they formed a stable, unchanging scaffold. On that scaffold, particles moved, collided, and interacted. This inertness was not considered a flaw, it was a feature. By keeping space subordinate, and physics could focus on what mattered most, matter and force, calculations became manageable, predictions became reliable. Planetary orbits could be computed with remarkable accuracy. Cannonballs followed predictable arcs. Tides rose and fell according to gravitational influence. The usefulness of this model cannot be overstated. For centuries it worked extraordinarily well. Even today, classical mechanics remains the foundation for engineering, architecture, and most everyday calculations. Bridges stand, satellites are launched, machines function. All of this depends on treating space as a stable, empty backdrop. There is a certain elegance in this simplicity. Space does not argue. It does not demand attention. It does not complicate equations. It offers a quiet consistency that allows physical laws to shine. In this sense, that emptiness was not just tolerated, it was embraced. It became the canvas upon which the universe painted its events. Yet this silence carried assumptions. By declaring space inert, classical mechanics quietly ruled out certain possibilities. Space could not store energy. It could not transmit influence on its own. It could not change shape or properties. If something happened, it happened because matter did something to matter, mediated by forces that acted across space but did not belong to it. This is where the mechanical view reveals its limits. It treats space as a container, not as a participant. It assumes that removing everything from a region leaves behind nothing of physical consequence, and as long as only solid objects and simple forces were considered, this assumption held. Even gravity, in Newton's formulation, fit comfortably into this picture, though not without unease. Gravity acted at a distance. Objects attracted each other through empty space, but space itself remained unaffected. It carried the force without contributing to it. This was puzzling even to Newton, who famously declined to speculate on the mechanism of gravitational action. He offered no explanation for how the influence travelled across the void, only the mathematical description of its effect. But the mathematics worked, and that was enough for the time. There is a quiet practicality to this approach. Physics does not demand metaphysical completeness, it demands predictive success, and the mechanical view of empty space delivered that success repeatedly. Its very silence made it powerful. At human scales, emptiness behaves exactly as this model predicts, and a spacecraft drifting between planets encounters almost no resistance. A stone thrown into the air follows a smooth arc. The vacuum inside a laboratory chamber allows experiments to proceed without interference from air. Space in these contexts appears to do nothing at all. This apparent inactivity reinforced the idea that emptiness was truly empty. If nothing happens there, then nothing must be there. The absence of obvious effects was taken as evidence of absence itself, but physics advances by paying attention to the quiet details, the subtle inconsistencies that linger at the edge of understanding. Over time, questions began to surface. If space is truly inert, how does light move through it? Light is not a material object, it has no mass, yet it travels at a fixed speed, the same for all observers regardless of their motion. That this behaviour sits uneasily within a framework that treats space as a passive background. There were also conceptual discomforts. If motion is measured relative to absolute space, why does that space never reveal itself directly? Why can it not be detected, pushed against, or disturbed? Newton himself acknowledged this unease even as he relied on the concept. Still, the mechanical view endured because it worked. Its success delayed deeper questions rather than answering them. And in science, delayed questions are not ignored questions, they wait. The silence of empty space, so useful and so convincing, eventually became something to listen to more carefully. As measurements grew more precise, a new phenomena entered the picture, especially those involving light and electromagnetism. The assumption of an inert backdrop began to strain. And for the moment, though, emptiness remained obedient. It held still. It allowed motion. It asked nothing in return, and that obedience made it one of the most productive ideas physics had ever adopted. Yet even as Newton's framework solidified, the seeds of its transformation were already being sown elsewhere, not in the grand motions of planets, but in the subtle behaviour of light and fields. The story of emptiness was about to become entangled with the nature of light itself, and with it, the proposal of a new, invisible occupant of space, an occupant meant to preserve the idea of a medium, yet one that would ultimately deepen the mystery of the void. Light has a habit of exposing assumptions. For centuries, it behaved just predictably enough to be useful, yet strangely enough to be unsettling. It reflected, refracted, scattered, and travelled at enormous distances, often through regions that appeared empty, and as understanding of light deepened, it began to place quiet pressure on the idea that empty space could be treated as nothing at all. In classical mechanics, motion required a background, but not a medium. A thrown stone did not need something to carry it forward. But waves were different. Sound waves needed air. Water waves needed water. Vibration seemed inseparable from the material that supported them. And light, as it was increasingly understood in the 18th and 19th centuries, behaved like a wave. This created an immediate problem. If light was a wave, then what was it waving in? It travelled through space between the sun and the earth, across vast regions where no air could exist. It crossed the apparent emptiness between stars and galaxies. If empty space truly contained nothing, then light had no obvious medium to support its motion. Rather than abandon the wave description, physicists introduced a solution that preserved both the intuition and mathematical consistency. They proposed the existence of the luminiferous ether. This ether was imagined as an invisible, all-pervading substance that filled all of space, including regions devoid of matter. It was not air, it had no weight. It offered no resistance to motion, yet it provided the necessary medium for light waves to propagate. The ether was appealing precisely because it solved multiple problems at once. It allowed light to behave like a wave without contradicting the assumption that space itself was inert. That empty space could remain empty of matter, while still being filled with a subtle substance that no one could see or feel. In this way, emptiness was preserved in name while quietly being filled in fact. Many prominent physicists embraced the idea. James Clerk Maxwell's equations of electromagnetism, developed in the mid-19th century, described light as oscillating electric and magnetic fields. These fields seemed to require a medium in which to exist. The ether fit neatly into this picture. It became the unseen stage on which electromagnetic phenomena played out. But the very qualities that made the ether attractive also made it deeply problematic. It had to be incredibly rigid to support the high speed of light, yet completely undetectable to motion. The Earth moving around the Sun at roughly 30 kilometers per second should have been ploughing through this ether constantly. If that were true, then the speed of light measured on Earth should vary depending on the direction of motion, much like the apparent speed of wind changes for a moving cyclist. Careful experiments were designed to detect this effect. The most famous of these was conducted by Albert Michelson and Edward Morley in the late 1880s. Their experiment compared the speed of light along perpendicular paths, expecting to observe slight differences caused by Earth's motion through the ether. The result was unsettling in its simplicity. No difference was detected. The speed of light appeared the same in all directions. Repeated experiments confirmed the finding. If the ether existed, as it was behaving in ways that defied explanation, this created a growing tension. On the one hand, the wave nature of light strongly suggested the need for a medium. On the other hand, every attempt to detect that medium failed. The ether was becoming increasingly elaborate in theory and increasingly absent in practice. Light's behaviour in empty regions sharpened the problem. Light did not slow down in interplanetary space. It did not scatter or attenuate in ways that suggested interaction with a substance. It travelled vast cosmic distances with remarkable consistency. Whatever space contained, it did not behave like any known material medium. There was also a conceptual discomfort. If the ether filled all space, then space was no longer empty in any meaningful sense. Emptiness had become a semantic illusion. The universe was full, after all, just filled with something conveniently invisible and conveniently unresponsive. This was a subtle shift. Emptiness was being preserved, not because evidence demanded it, but because abandoning it felt premature. The ether was doing the quiet work of protecting a familiar picture of space as a passive container. At the same time, light continued to behave in ways that strained this picture. Its speed appeared to be a fundamental constant rather than a property of motion through a medium. Observers moving at different velocities all measured the same value. This was unlike sound, unlike water waves, unlike anything else, understood as a vibration of matter. The more precisely light was studied, the less cooperative the ether became. Adjustments were proposed. Perhaps the ether was partially dragged along by the Earth. Perhaps it contracted object as moving through it. These ideas added complexity without adding clarity. There is a gentle lesson here. When a concept exists primarily to protect an assumption, it becomes fragile. The ether existed to protect the idea that empty space must be inert, but as evidence accumulated, that protection began to feel forced. Light did not merely travel through empty space. It seemed to define something about space itself. Its speed set limits. Its behavior revealed structure. It forced physicists to ask whether the emptiness they had relied on was truly as simple as it appeared. By the end of the 19th century, the situation was clear but unresolved. Light behaved like a wave, yet no medium could be found. An empty space seemed to support electromagnetic phenomena without behaving like a substance. The mechanical view of space was under strain, not because it had failed outright, but because it had grown too quiet to explain what was being observed. Light had complicated emptiness without announcing a solution. It had introduced cracks rather than collapse, but once those cracks appeared, the idea that space was merely an empty stage could no longer be taken for granted. Something about space itself was beginning to matter. The stage was set for a more radical reimagining, one that would not fill space with a new substance, but would instead reshape the very concepts of space and time, binding them together into a new entity called Spacetime. And in that reshaping, her emptiness would gain a structure more profound and more active than anyone had previously imagined. The late 19th century was a time of quiet crisis in physics. On the surface, everything worked. Newton's mechanics described the motion of planets and projectiles with breathtaking precision. Maxwell's equations unified electricity and magnetism, predicting electromagnetic waves that travelled at the speed of light. The universe seemed orderly, deterministic, and almost fully understood. But beneath this calm surface, two deep problems were quietly pulling the foundations apart. One was the strange, unwavering constancy of the speed of light. The other was the persistent, undetectable ether. These were not separate issues, they were two sides of the same troubling coin. If light was a wave, it needed a medium. Yet every attempt to find that medium, to measure our motion through it, to feel its presence, and to detect its influence came up empty. The ether was becoming a ghost, a necessary idea that refused to materialize. Albert Michelson was one of the physicists determined to find this ghost. Skilled in the art of precision measurement, particularly with light, Michelson designed an experiment of exquisite sensitivity. Alongside Edward Morley, he built an instrument called an interferometer. Its purpose was straightforward: to detect the Earth's motion through the luminiferous ether. The logic was simple and inescapable. If the ether filled all of space and was stationary, then the Earth, orbiting the Sun at about 30 kilometers per second, was moving through it. This motion should create an ether wind, much like a cyclist feels a wind even on a still day. A beam of light travelling with this wind should go slightly faster than a beam travelling across it. The difference would be tiny, a fraction of a percent of the speed of light, but not beyond measurement. Michelson and Morley's interferometer was a masterpiece of precision. A single beam of light was split in two. Each half travelled down a perpendicular arm of equal length, reflected off a mirror, and returned to recombine. If the light took different times to travel along the two paths, the recombined beams would be out of step, creating an interference pattern, a series of light and dark bands. By rotating the apparatus, they could change the orientation of the arms relative to the supposed ether wind. The interference pattern should shift in a predictable, measurable way. They isolated the apparatus from vibrations. They conducted the experiment at different times of day and different seasons, as Earth's direction of motion changed. They took every precaution, reached the limits of their instrumentation's sensitivity, and they found nothing. No shift, no change. The interference pattern remained stubbornly, perfectly still. The speed of light was exactly the same in every direction, regardless of how the Earth was moving. The expected signal simply wasn't there. This was not a minor discrepancy. It was a null result of profound significance. Physics is comfortable with unexpected results, but it is rarely comfortable with nothing happening when something must happen if a theory is correct. The Michelson-Morley experiment did not merely fail to confirm the ether, it actively undermined it. At first, physicists attempted salvage operations. Perhaps the ether was dragged along by the Earth. Perhaps objects contracted slightly in the direction of motion, just enough to cancel out the effect. These explanations, like those proposed by Hendrik Lorentz and George Fitzgerald, were mathematically clever but physically strained. They explained the result without explaining why it should occur. They were fixes, not insights. What made the situation more serious was repetition. Variations of the experiment were performed again and again with increasing precision. The outcome remained the same. Light behaved as if no medium existed, or more precisely, as if space itself imposed the same rules everywhere regardless of motion. This forced a re-evaluation of what emptiness meant. Guilds. But the absence of the ether was no longer something that could be dismissed as ignorance or experimental limitation. It was now a consistent, reproducible result. Emptiness was not just what remained when something could not be found. It was what the data actively supported. There is an important distinction here. Science does not treat absence lightly. Failing to detect something once is rarely meaningful. Failing to detect something repeatedly, under conditions where it must appear if it exists, becomes powerful evidence. The Michelson-Morley experiment turned emptiness into a measurable claim. It revealed something unexpected about motion through space. Motion did not seem to be defined relative to a hidden background. There was no preferred state of rest. No invisible substance marked out absolute stillness. Instead, the laws governing light appeared the same for all observers, regardless of how they moved. This was not a philosophical conclusion. It was an experimental one. Space did not behave like a medium. It did not carry traces of motion. It did not provide resistance, drag, or direction. The old idea of absolute space filled with an unseen substance was becoming untenable. What replaced it was not immediately clear. The experiment told physicists what space was not, but not yet what it was. Still, that negative knowledge mattered immensely. The collapse of the ether was not dramatic or explosive, it was quiet. A steady accumulation of null results that refused to go away. There is a certain calm, honesty in this moment. Physics did not declare victory, it did not announce a new truth immediately, and it simply accepted that a long-held assumption no longer fit the evidence. Emptiness, once treated as a placeholder for ignorance, now demanded to be taken seriously as a physical condition. The failure of the ether also sharpened a deeper question. If light did not need a medium, then perhaps the assumption that waves always require one was wrong, or perhaps space itself had properties that had not yet been recognized. Either way, the idea of space as a passive, inert backdrop was under immense pressure. The Michelson-Morley experiment did not solve the problem of emptiness. It transformed it. It marked the point where emptiness stopped being something to fill with convenient substances and became something to understand on its own terms. In removing the ether, the experiment did not return physics to a simpler view, and it opened the door to a more radical one, a view in which space and motion could no longer be separated so easily, a view in which the structure of space itself might matter. The silence of the experiment spoke clearly. Whatever space was, it was not a hidden ocean carrying light along. Whatever emptiness meant, it could no longer be dismissed as a failure to look hard enough. It was real, it was measurable, and it was about to demand a completely new description. Into this uncertainty stepped a young patent clerk in Bern, Switzerland. Albert Einstein was not looking for a new substance to fill space. He was thinking deeply about the nature of light, motion, and time. In 1905, he published a paper that would later be called the theory of special relativity. It did not begin with a description of what space is made of. Instead, it began with two deceptively simple principles, grounded in the experimental facts of the day. First, the laws of physics are the same for all observers moving at constant velocity. Second, the speed of light in a vacuum is the same for all such observers, regardless of how they move. These principles were not invented to be provocative. They were an attempt to take the Michelson-Morley result at face value and follow it to its logical conclusion. Einstein accepted that the speed of light was a constant universal limit. He asked, what must be true about space and time for this to be possible? The answer was a radical shift. Space and time, once treated as separate and absolute, could no longer remain independent. They were woven together into a single fabric, space-time. In this new picture, measurements of distance depended on motion. Measurements of time depended on motion. Two observers moving relative to one another could disagree about how long something took or how far apart two events were, and both could be correct. This was not because measurement tools were flawed, but because space and time themselves were intertwined. Events that appeared simultaneous to one observer might not appear simultaneous to another. Lengths could contract. Clocks could tick at different rates. These effects were not optical illusions or mechanical failures. They were intrinsic properties of reality, consequences of the fixed, finite speed of light. To describe this coherently, physicists began to speak of spacetime. Spacetime is not simply space plus time, and it is a unified four-dimensional structure in which distances and durations are linked. An event is no longer described only by where it happens, but also by when it happens. Together, these coordinates form a single description in the geometry of spacetime. This unification changed the meaning of emptiness forever. Empty space was no longer just a region without matter. It was a region with a specific spacetime structure. Even when nothing occupied it, spacetime still existed. It still had measurable properties. It still constrained what could happen within it. One of the most striking consequences of special relativity is that empty space now imposes limits. The speed of light acts as a universal maximum speed, not because light struggles against resistance, but because spacetime itself is structured in such a way that this speed cannot be exceeded. This limit exists even in a perfect vacuum, even in the absence of matter. Spacetime enforces rules. This alone is enough to show that emptiness is not nothing. A region that restricts motion, defines simultaneity, and links space to time is not inert in the classical sense. It may not be filled with particles, but it is not passive. Another profound shift followed naturally. If space and time are intertwined, then measurements depend on the observer. Emptiness, once assumed to be absolute, becomes relative. Two observers moving differently through the same region of spacetime may not agree on its dimensions or duration. The space between 2 points can be shorter for one observer and longer for another. The time between two events can stretch or compress depending on motion. This does not mean reality becomes subjective. The underlying spacetime structure remains consistent. What changes is how that structure is sliced into space and time by different observers. Emptiness has a geometry, but that geometry is not experienced identically by everyone. This idea can feel unsettling, but it is grounded firmly in experiment. Time dilation has been measured using precise atomic clocks flown on aircraft and satellites. Length contraction plays a role in the behavior of fast-moving particles in accelerators. These are not abstract predictions. They are practical, measurable consequences of space-time structure. Einstein's work also quietly resolved a lingering discomfort from classical mechanics. Absolute space, but which could never be detected directly, was no longer needed. Motion no longer had to be measured relative to an invisible background. Instead, motion was defined relative to other observers, all governed by the same physical laws. This did not make space disappear. It made it richer. Space became part of a dynamic framework rather than a silent container. Even in the absence of matter, space-time retained its structure. It defined what paths were possible. It determined how clocks behaved. It shaped the behavior of light. There is a gentle irony here. In removing the ether, physics did not return to emptiness as nothing. It replaced one unseen medium with a deeper, more abstract structure. Space-time does not behave like a substance. But it is not nothing either. It can be measured, modelled and tested. It has geometry, it has limits. It has consequences. This new view also softened the question of emptiness rather than answering it outright. Asking whether space is empty now requires asking empty of what? Empty of matter, perhaps? Empty of energy? Not necessarily. Empty of structure? Certainly not. Special relativity revealed that even a perfect vacuum carries information about motion and causality. It defines which events can influence which others. It determines how signals propagate. It encodes relationships that exist regardless of whether particles are present. In this sense, emptiness becomes contextual. A region may be empty of atoms yet full of space-time relationships. It may contain no particles, but still enforce cosmic speed limits and temporal order. This, however, was only the beginning. That special relativity reshaped how motion and time were understood, but it left gravity untouched. Gravity, still described by Newton as a force acting instantaneously across space, remained awkwardly separate. If space-time defined motion, then gravity's role within that structure demanded rethinking. Einstein would not leave that problem alone for long. Over the next decade, he worked to extend the principles of relativity to include gravity. The result would be general relativity, a theory that would not only describe gravity as geometry, but would also transform emptiness once more, giving it curvature, ripples, and a dynamic personality. The quiet revolution of special relativity did not make space noisy or dramatic. It made it meaningful. Empty space was no longer a void waiting to be filled. It was a framework with rules, limits, and geometry. And once that framework existed, the idea that gravity might be a feature of space-time itself became not just possible but inevitable. Emptiness had acquired structure, and with structure came the possibility that it could bend, stretch, and change. The stage was no longer rigid and absolute. It was flexible, responsive, and alive with potential. The realization that space and time were woven together into a single entity, space-time, marked a point of no return in the story of emptiness. Emptiness could no longer be imagined as a mere absence, a blank stage waiting for actors. It was now a structured medium, a flexible geometry that defined the very rules of motion and causality. But one profound force remained outside of this new picture: gravity. In Newton's universe, gravity was a mysterious force that acted instantaneously across empty space, pulling objects together without any visible mechanism. It worked with breathtaking precision, but it felt like an add-on, a rule imposed upon space rather than emerging from it. For Einstein, this disconnect was deeply unsatisfying. If space-time was the true fabric of reality, then gravity must be a feature of that fabric, but not a guest passing through it. For 10 years, from 1905 to 1915, Einstein wrestled with this problem. The outcome was the theory of general relativity, a radical reimagining of gravity not as a force, but as the geometry of space-time itself. In this picture, matter and energy do not simply sit in space, they shape it. A massive object like the Sun warps the space-time around it. Other objects, like planets, then move along the natural paths within that curved geometry. What we perceive as gravitational attraction is simply the motion of objects following the contours of bent space-time. A common analogy involves a stretched rubber sheet. Place a heavy ball in the center, and the sheet dips. A smaller marble rolled nearby will curve inward, not because it's being pulled by a force, but because it's rolling along a sloped surface. The analogy is imperfect. Space-time curvature occurs in 4 dimensions, not at 2, but it captures the essence. Gravity is not something added to space. It is how space itself is shaped. This shift has profound implications for emptiness. In Newtonian physics, empty space was flat, uniform, and inert. In general relativity, empty space can be curved. Geometry no longer depends solely on the presence of matter at every point. It can exist independently, carrying the imprint of distant masses, or even persisting on its own. This is one of the most counterintuitive aspects of modern physics. A region of space can be utterly empty of matter, and yet still possess curvature. That curvature can influence motion, bend the paths of light, and shape the behavior of anything passing through, even if nothing occupies the region itself. This idea is not hypothetical, it is observed. One of the first and most dramatic confirmations of general relativity came during a solar eclipse in 1919. Astronomers led by Arthur Eddington measured the positions of stars near the Sun's edge. According to Einstein's theory, the Sun's mass should curve the space-time around it, causing light from distant stars to bend as it passes nearby. The observed shift in the stars' positions matched the prediction precisely. The light was travelling through space that was empty of matter, the near vacuum of the interplanetary space, yet its path curved because space-time itself was curved by the Sun's presence. Emptiness was not a passive stage, it was a flexible geometry that guided light itself. Even more strikingly, general relativity allows for solutions in which space-time curvature exists entirely without matter. These are known as vacuum solutions to Einstein's field equations. The equations governing space-time do not require matter to be present everywhere for curvature to exist. They allow geometry to propagate and persist on its own. The most famous example of this is gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, produced by violent cosmic events like merging black holes or neutron stars. Once created, these waves travel outward at the speed of light, passing through vast regions of empty space. They stretch and compress space-time as they move, even when no particles are present. For a century, gravitational waves were a theoretical prediction. Then in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection. What was detected was not matter, not radiation, but a subtle oscillation in space-time geometry, a passing ripple in emptiness itself. Empty space was actively, measurably oscillating. This reveals something subtle but essential. Emptiness in general relativity is not defined by flatness. It is defined by the absence of matter and non-gravitational energy. Geometry remains, structure remains, rules remain. This is why gravity, in this framework, is not a force inside space but a feature of space. Objects respond to geometry rather than being pulled through a void. Free-falling objects follow the straightest possible paths through curved space-time, paths known as geodesics. These paths exist whether or not the region contains matter. There is a quiet elegance to this idea. Gravity becomes less like an invisible hand and more like the shape of the landscape. Space tells matter how to move and matter tells space how to curve, but once the curvature exists, it does not vanish when matter leaves. It carries history. This challenges the intuition that emptiness must be simple. An empty region near a star is not the same as an empty region far from all mass. Both may contain no particles, but their geometries differ. Light behaves differently. Time passes at different rates. Motion unfolds along different paths. Even time itself becomes uneven. Clocks placed at different positions in a gravitational field tick at different rates, a phenomenon known as gravitational time dilation. So this effect has been measured repeatedly and must be accounted for in technologies like the Global Positioning System. Once again, empty space proves capable of influencing physical processes. It is not a neutral backdrop, it is an active participant, shaping the flow of time itself. There is a gentle irony here. The more physics removes matter, the more space itself steps forward. What began as an empty stage becomes an active structure. What was once assumed to be nothing turns out to be the very thing shaping motion, light, and time. Importantly, general relativity does not claim that space is filled with a hidden substance. It does not revive the ether in a new form. Space-time curvature is not a material medium. It does not provide resistance. It does not define a preferred frame of rest. It simply has geometry, and that geometry matters. This distinction preserves the lessons of earlier experiments. There is no absolute background against which motion is measured, yet there is still a real physical structure governing how events unfold. Emptiness is neither a void nor a substance. It is a geometric condition. At this point, the idea of empty space has changed completely from its original meaning. It is no longer defined by the absence of influence. Empty space influences motion. It shapes trajectories, it limits possibilities, it carries waves, and still, something is missing. General relativity describes geometry beautifully, but it says little about energy in regions completely devoid of matter. It treats space-time as shape, not as a reservoir. So the question of whether empty space contains energy of its own remains open at this stage. Curved space can exist without matter, but curvature itself may carry something more subtle. The geometry of emptiness is established, but its energetic content has not yet been fully addressed. Emptiness, now undeniably structured, quietly invites the next question. If space can bend and ripple without particles, can it also store energy without them? And if so, what kind of energy would that be? The stage is no longer silent, but it is not yet finished speaking. While Einstein was reimagining gravity, another quiet revolution was already woven into the fabric of physics, one that began not with planets or light, but with the invisible lines of force that surround magnets and charges. Long before space-time was understood to curve, the space itself had begun to acquire occupants that were neither particles nor substances. These occupants were known as physical fields. A field is not an object you can hold. It is not a material that flows or accumulates. Instead, a field assigns a value, a number, a direction, a potential, to every point in space and time. It describes what would happen if something were placed there. A magnetic field tells you how a compass needle would turn. An electric field tells you how a charged particle would accelerate. Even when no particle is present, the field still exists. This idea was most clearly developed in the 19th century by Michael Faraday. Faraday was not primarily a mathematician. He thought visually and experimentally. He introduced the concept of lines of force, and imagining space itself threaded with invisible structures that guided electrical and magnetic effects. To Faraday, these lines were not just helpful drawings, they were real features of space. This was a radical step. Instead of forces acting instantaneously across empty space, influences were carried locally by fields that filled the region between objects. Space was no longer just the place where interactions happened, it became the medium in which those interactions were encoded. James Clerk Maxwell took Faraday's intuition and gave it mathematical form. In the 1860s, Maxwell unified electricity and magnetism into a single framework now known as classical electromagnetism. His equations showed that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. Together, they can sustain one another, forming electromagnetic waves. Light itself emerged naturally from this picture. Maxwell's equations predicted waves that travelled at a fixed speed, determined by electric and magnetic properties, a speed that matched the measured speed of light. Light was no longer a mystery substance or a mechanical vibration, it was an oscillation of fields. Crucially, these fields did not require particles to exist. An electromagnetic field can occupy a region of space even if no charged particles are present there. The field is not created anew each time a particle passes through. It already exists as a condition of space itself, shaped by boundary conditions and sources elsewhere. This has an important consequence for emptiness. A region of space can be empty of matter and still contain fields. And those fields can store energy, transmit influence, and affect anything that enters the region later. Empty space, in this sense, is already structured before anything arrives. Field energy is not abstract, it can be measured and accounted for. The energy stored in an electric field between two charged plates can be calculated and released. A magnetic field carries energy that can exert pressure even in regions far from any source. Residual fields can persist long after their sources are gone. This shifts the meaning of emptiness yet again. Removing particles does not remove structure. It does not return space to a neutral background. Instead, space retains a pattern of possibilities. It defines how particles would behave if they were present, even when they are not. There is a gentle clarity to this idea. The fields do not demand attention. They are not loud, they do not clutter space with objects. They simply exist everywhere, allowed by the laws of physics, quietly defining the rules of interaction. In classical physics, fields were treated as continuous quantities. Their values changed smoothly from point to point. They could be strong or weak, curved or straight, but they did not come in discrete pieces. This continuity made them feel less like objects and more like conditions, background presences that were always there waiting to be felt. And yet their presence was undeniable. Without fields, forces had no mechanism. Without electromagnetic fields, light had no description. Without gravitational fields, motion lost its guide, fields became indispensable. So this also resolved a lingering discomfort. Forces no longer had to leap across empty space instantaneously. They could propagate at finite speeds through fields that occupied the intervening region. Space was no longer empty between interacting objects. It was filled with the very structures that made interaction possible. At the same time, fields did not behave like the abandoned ether. They did not define a preferred state of rest. They did not resist motion uniformly. They were compatible with relativity. Their behavior depended on observers, but their existence did not privilege any particular frame. This compatibility mattered. It allowed fields to coexist naturally with the spacetime picture introduced by Einstein. Fields lived in spacetime. They evolved over time. They respected the limits imposed by the speed of light. That they fit. Still, classical fields carried an implicit assumption. They were smooth, continuous, and infinitely divisible. At every point, a value could be defined with arbitrary precision. This assumption would not survive indefinitely. As measurements became more precise and scales became smaller, cracks appeared. Energy exchanges occurred in discrete amounts. Light behaved like both a wave and a particle. Fields, once thought to be smooth fabrics, began to show grain. But before that transition, fields performed a crucial role. They established that empty space is not empty of physical content. It is filled with conditions, structures, and stored possibilities. Even without matter, space is already busy defining how matter will behave when it arrives. This makes fields a natural bridge between classical and quantum thinking. They retain the continuity and calm of classical physics while quietly preparing the ground for something more restless. They show how structure can exist without substance, how influence can persist without objects. By the time particles are removed, something always remains. Geometry remains, fields remain, rules remain. Empty space, once imagined as a blank canvas, has become a textured one, not crowded, not noisy, but undeniably present. And with fields occupying every region where physics allows them to exist, emptiness takes on a new character. It is no longer the absence of everything, but the presence of what cannot be seen. This realization does not yet require quantum mechanics. It simply requires accepting that space itself carries more than location. It carries information, structure, and stored influence. And that acceptance quietly sets the stage for the next transformation, one that will not only fill space with fields, but will also make those fields restless, fluctuating, and fundamentally uncertain. The calm, continuous fields of the 19th century are about to give way to a quantum vacuum, where emptiness is not just structured, but intrinsically, unavoidably active. The journey into the heart of nothingness is about to descend to the smallest scales, where the very concept of stillness dissolves into a sea of perpetual motion. By this point, emptiness has already lost much of its original simplicity. Space can curve, fields can exist without particles, geometry can guide motion even where nothing tangible is present. But one idea still resists intuition more than most. The idea that energy itself can exist without objects. In everyday experience, energy feels inseparable from things. A moving car has energy because it has mass and speed. A hot stove has energy because its atoms are vibrating. A stretched spring stores energy because it can snap back. Energy seems always tied to matter doing something. This intuition is useful but incomplete. In physics, energy is not defined by objects alone. It is defined by the capacity to cause change. Anything that can influence motion, temperature, structure, or interaction is said to carry energy, though whether or not it is attached to a solid object. Fields make this clear almost immediately. An electric field stores energy, even if no charged particle is moving through it. A magnetic field can exert pressure, transfer momentum, and do work. That energy does not vanish simply because the field is temporarily empty of particles. It remains distributed throughout space. This is not a metaphor. It is measurable. The energy stored in an electric field between charged plates can be calculated and released. The energy density of a magnetic field can be detected through its effects. Space itself, structured by fields, becomes a reservoir. Gravity adds another layer of subtlety. In general relativity, gravity is geometry rather than force, which makes gravitational energy difficult to localize. There is no single point where gravitational energy sits. Instead, it is associated with the curvature of spacetime as a whole. Despite this difficulty, gravity clearly carries energy. Gravitational waves transport energy across the universe. As they pass through space, they stretch and compress distances, doing work on anything they encounter. Detectors on Earth have measured this effect directly. The energy arrives not as particles, not as radiation, but as changes in spacetime itself. What matters here is not the bookkeeping challenge, but the implication. Empty space shaped by gravity can carry energy without containing matter. The energy is not stored in objects. It is stored in structure. This challenges everyday logic because human intuition evolved in a world where energy was always attached to something visible. Fires burned fuel, muscles burned food, rivers flowed down Gold Hill. Energy appeared only when matter moved or transformed. Physics reveals a broader picture. Energy can be spread out. It can be diffuse. It can exist as tension, curvature, or configuration. It does not need a container in the ordinary sense. This becomes especially clear when considering gravitational binding energy. When two massive objects attract each other, the system as a whole has less energy than the objects would have if they were infinitely far apart. That difference is energy associated with the gravitational field between them. Remove the objects and the energy accounting changes, but while they exist, the energy is not sitting inside either object alone. It belongs to the space between them. Fields behave similarly. An electromagnetic wave travelling through empty space carries energy and momentum. It can heat surfaces, push objects, and trigger chemical reactions. That energy exists while the wave passes through regions containing no matter at all. At this stage, emptiness no longer looks passive. Even stripped of particles, space remains capable of storing, transmitting, and redistributing energy. It can act. This is not a violation of conservation. Energy is still conserved, it is simply not confined to objects. Conservation laws apply to systems that include space itself as a participant. There is a quiet shift in perspective here. Instead of asking where the energy is stored, physics asks how energy is distributed. That distribution often includes regions that appear empty. This shift also explains why emptiness resists being fully cleared. Removing matter removes one carrier of energy, but it does not remove fields, geometry, or motion itself. Each layer peeled away reveals another layer beneath it. There is a temptation to imagine that once matter is gone, nothing meaningful remains. Physics consistently refuses this simplification. Even when particles are absent, the conditions that define how particles will behave remain in place. Those conditions have energetic consequences. This does not mean that empty space behaves like a battery waiting to discharge. It means that space participates in physical law. It enforces limits. It carries influences. It responds to change. At larger scales, this idea becomes unavoidable. The expansion of the universe involves energy associated with space itself. Gravitational waves cross cosmic voids. The light travels for billions of years through regions nearly devoid of matter, carrying energy the entire time. At smaller scales, the same principle applies. Even before quantum mechanics enters the picture, classical physics already demands that emptiness be energetically active. This realization unsettles a simple mental shortcut. The shortcut says that energy requires stuff. Physics replies that energy requires structure, and structure does not vanish when matter does. There is a certain calm honesty in this. Nature does not make special allowances for intuition. It follows consistent rules, whether those rules feel comfortable or not. Emptiness, as it turns out, follows rules too. By now, empty space has acquired geometry, fields, and energy. It is no longer reasonable to think of it as a void. It is a participant, and even when it appears still, and yet everything described so far remains within the framework of classical physics. Fields are smooth. Energy can be continuous. Space, while structured, behaves predictably at every scale considered so far. This calm will not last indefinitely. As attention turns towards smaller scales and higher precision, a new kind of restlessness appears. Energy exchanges become discrete. Fields begin to fluctuate. Emptiness itself starts to exhibit activity that cannot be smoothed away. The idea that energy can exist without objects is not the end of the story, it is the threshold. Once energy is allowed to exist independently of matter, the question naturally follows: if energy is allowed everywhere, even in emptiness, what prevents it from appearing, disappearing, or fluctuating at the smallest scales? That question belongs to quantum mechanics, and once it is asked, emptiness becomes something far stranger than a quiet background. By the early 20th century, physics had already learned to be cautious about stillness. Space could curve, fields could persist without particles, energy could exist without objects. Yet there remained a comforting assumption beneath all of this. If everything were removed, if motion ceased, if energy were minimized, then perfect rest should be possible. A true quiet, a final calm. Quantum mechanics quietly removed that possibility. Quantum mechanics is not a small correction to classical physics. It is a framework built to describe nature at very small scales, where atoms, electrons, and photons dominate behavior. And it emerged not from philosophical preference, but from repeated experimental failures of classical ideas. Certain phenomena simply refuse to behave smoothly or continuously. One of the most important figures in shaping this framework was Werner Heisenberg. In 1927, Heisenberg articulated what became known as the uncertainty principle. This principle does not describe a limitation of instruments or technique. It describes a limitation built into nature itself. At its heart, the uncertainty principle states that certain pairs of physical quantities cannot both be known with arbitrary precision at the same time. The most famous pair is position and momentum. The more precisely the position of a particle is known, the less precisely its momentum can be known, and vice versa. This is not because measurement disturbs the system in a clumsy way, it is because particles do not possess exact values for these quantities simultaneously. The uncertainty is not something added by observation, it is something that exists before any observation takes place. This immediately challenges the idea of perfect rest. Rest implies a particle with precisely zero momentum sitting at a perfectly defined position. Quantum mechanics forbids this combination. If a particle were perfectly localized, its momentum would become highly uncertain. If its momentum were precisely zero, its position would spread out. There is no way around this. It is not a matter of clever setup or improved equipment. It is a structural feature of the quantum world. This means that at small scales, stillness is not an available state. A motion in some form always remains. Even in the lowest possible energy state, known as the ground state, particles retain residual motion. This is often referred to as zero-point energy. Zero-point energy does not mean that energy is arbitrarily large. It means that energy cannot be reduced to nothing. There is a minimum, a floor beneath which systems cannot descend. This is easy to overlook because everyday objects average over enormous numbers of particles. The restless motion of individual atoms cancels out at large scales. A table feels solid and still, a room feels calm. But at the microscopic level, motion persists relentlessly. This persistence has measurable consequences. Atoms do not collapse because electrons retain motion even in their lowest energy states. Molecules do not freeze into rigid structures at absolute zero. Quantum fluctuations prevent total stillness. What matters here is not the details of atomic structure, but the principle behind them. Quantum mechanics does not allow perfect rest. It replaces it with the lowest possible activity. This shifts the meaning of emptiness once again. Even if all particles were removed from a region, the quantum rules governing particles do not disappear, the framework remains, and that framework forbids complete stillness. Uncertainty in this context is not ignorance. It is not a statement about what humans know, it is a statement about what exists. A particle does not secretly have a precise position and momentum waiting to be discovered. Those quantities are genuinely indefinite until constrained by interaction. This distinction is essential. For a long time, physicists hoped that uncertainty reflected missing information. Perhaps deeper variables existed beneath quantum mechanics. Perhaps nature was deterministic after all, and uncertainty was only apparent. Experiments repeatedly ruled this out. Tests of quantum correlations, including those inspired by John Bell in the 1960s, showed that no local hidden variable theory could reproduce the observed results. Uncertainty was not a temporary placeholder, it was fundamental. This has direct consequences for emptiness. If uncertainty governs all physical systems, then empty space cannot be perfectly calm. Even the absence of particles does not exempt a region from quantum rules. At this stage, the idea of a quiet vacuum becomes suspect. Classical intuition suggests that removing particles removes activity. Quantum mechanics suggests otherwise. Activity does not require particles to be present in a persistent way. It can emerge transiently, fluctuate, and vanish again, constrained only by uncertainty. It is important to be precise here. Quantum mechanics does not say that anything can happen anywhere at any time. The uncertainty principle sets strict limits. Fluctuations are constrained. Energy must still be conserved on average. Effects are subtle, but subtle does not mean negligible. The fact that perfect rest is forbidden means that emptiness cannot be fully emptied. There is always a baseline level of activity allowed by the rules of the theory. This is deeply counterintuitive. Human experience associates quiet with absence, silence with nothing happening. But quantum mechanics replaces silence with a kind of whisper, not loud enough to notice directly, but never completely gone. There is a gentle humour in this if one allows it. Nature seems unwilling to sit still even when given the chance. Remove everything and it fidgets anyway. This restlessness does not announce itself dramatically. It does not create explosions or visible motion. It exists at scales far removed from everyday experience, yet it has consequences that accumulate. The uncertainty principle also introduces a new way of thinking about limits. Classical physics often asks what happens if something is reduced to zero. Zero velocity, zero temperature, zero energy. Quantum mechanics replaces zero with minimum, the smallest allowed value, the lowest possible state. This minimum is not arbitrary. It emerges from the structure of the theory itself. It is as fundamental as conservation laws. By this point, that emptiness has been transformed repeatedly. It has gained geometry, fields, and energy. Now it gains irreducible motion, a baseline activity that cannot be removed. Quantum mechanics does not yet tell us exactly what empty space does. It tells us what empty space cannot do. It cannot be perfectly still. It cannot be perfectly defined. It cannot be a silent void. This realization prepares the ground for a more explicit picture of vacuum behavior. If uncertainty forbids stillness, then even the vacuum defined as the lowest energy state of a system must exhibit activity. That activity is not chaos. It is structured. It follows rules. It respects limits. But it is real. The idea of nothing is now under serious pressure. Once uncertainty is accepted as fundamental, emptiness can no longer be imagined as a calm endpoint. Thus, it becomes a dynamic condition, constrained but restless. And it is within that restlessness that the seemed vacuum begins to reveal its true character. Once quantum mechanics forbids perfect stillness, emptiness takes on a new and more precise meaning. Physicists do not abandon the idea of a vacuum. They redefine it. The vacuum becomes not the absence of everything, but the lowest possible energy state allowed by the laws of nature. This is what is meant by the quantum vacuum. In everyday language, a vacuum suggests removal. Take everything out, and what remains is nothing. In quantum physics, the vacuum is not what remains after everything's removed. It is a specific state, the ground state of a system, the configuration with the least energy permitted, but not zero energy. This distinction matters. The quantum vacuum is not empty in the classical sense. It is a condition of fields rather than particles. Even when no particles are present, the fields themselves remain, and they cannot be completely still. This view comes most clearly from quantum field theory, the framework that combines quantum mechanics with the concept of fields. In quantum field theory, particles are not fundamental objects floating through space. They are excitations of underlying fields. An electron is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. The fields come first. Particles are what fields do when energy is concentrated. This idea emerged gradually in the early 20th century. One of the key figures in this transition was Paul Dirac. Dirac worked to merge quantum mechanics with special relativity, and in doing so he helped formalize the idea that fields themselves must be quantized. Energy could not vary continuously at small scales. It came in discrete amounts. Quantizing a field means treating each mode of the field like a quantum system with allowed energy levels. Even the lowest level, the ground state, carries energy. This is not an optional feature. It arises directly from the uncertainty principle. If a field were to have exactly zero energy, its value and its rate of change would both need to be precisely defined. Quantum mechanics forbids that. The field must fluctuate even in its lowest state. This leads to a quiet but profound conclusion. Empty space, defined as a region with no particles present, is still filled with fields. And those fields, even in their ground states, fluctuate. These fluctuations are not large, that they do not pile up into visible motion. They are constrained tightly by quantum rules, but they are real. This is why physicists describe the quantum vacuum as restless. Not chaotic, not violent, but never perfectly still. Energy briefly appears in one form and disappears in another, constrained by uncertainty and conservation laws. It is important to be careful here. Popular descriptions often speak of particles popping in and out of existence. This language is useful but imprecise. What actually fluctuates are fields. The particle picture is a way of describing certain interactions, not a literal swarm of objects appearing from nothing. The vacuum in quantum field theory is a seething background of potential, a baseline activity that never quite shuts off. It is not empty in the sense of absence, and it is empty only in the sense that no lasting excitations are present. This distinction helps avoid confusion. The quantum vacuum does not violate conservation of energy. Over time, energy remains balanced. Fluctuations are temporary and constrained. They do not allow free energy extraction or spontaneous creation of matter without cause. Yet despite these limits, the vacuum has observable consequences. The lowest energy state of a field influences how particles behave. It shifts energy levels, it modifies forces, it affects decay rates. This means the vacuum is not a passive backdrop. It participates in physical processes even when nothing appears to be happening. There is a subtle change in perspective here. Instead of asking what exists in empty space, physics asks what state the fields are in. That emptiness becomes the statement about configuration, not absence. This also explains why removing particles does not simplify the universe as much as intuition suggests. Particles are only one expression of deeper structures. Beneath them lie fields that cannot be removed without removing the framework of physics itself. The quantum vacuum is the state of those fields when they are as calm as the rules allow, and that calm still contains motion. This idea can feel unsettling because it removes the concept of absolute nothingness. There is no switch that turns reality completely off. There is always at least a hum. Yet this hum is not arbitrary. It is tightly regulated. The vacuum does not explode with energy. It does not collapse into chaos. Its fluctuations average out. Their effects are subtle, cumulative, and precise. And one way to understand this is to imagine a perfectly calm lake that can never be completely flat. No matter how still the air, tiny ripples persist. They are not caused by wind or disturbance. They arise from the water itself, responding to unavoidable constraints. The lake is calm but not frozen. The quantum vacuum behaves in a similar way. It is the calmest state possible, not the quietest one imaginable. This framework resolves several earlier puzzles. Fields no longer require a classical medium. Light does not need an ether. Electromagnetic waves propagate as excitations of the electromagnetic field, which exists everywhere space-time allows. It also explains why emptiness resists being emptied even after removing matter, air, radiation, and heat. The underlying fields remain. Their ground states remain. Their fluctuations remain. At this point, emptiness has become something precise and technical. It is no longer a vague absence. It is a well-defined physical state with measurable properties. And yet everything described so far has remained largely theoretical. The quantum vacuum is a consequence of the mathematics. It is required for consistency. But physics demands more than internal coherence. It demands contact with observation. The natural next question is simple. If the vacuum is restless, does that restlessness do anything measurable? The answer is yes. The quantum vacuum does not merely exist as a conceptual necessity. It leaves fingerprints on the physical world. It shifts forces. It alters energy levels. It produces effects that can be detected under carefully controlled conditions. The vacuum, that once redefined as the lowest energy state of quantized fields, is no longer invisible. It is subtle, but it is active. And when its activity is isolated, constrained, or shaped, it begins to reveal itself. The transition from theory to effect has already begun. Once the quantum vacuum is understood as the lowest energy state of fields, a natural question follows. If fields can never be perfectly still, what does that restlessness look like? The answer is subtle, restrained, and far less dramatic than popular imagery suggests. It is known as vacuum fluctuation. Vacuum fluctuations are not explosions in empty space. They are not storms of activity or bursts of chaos. They are small, fleeting variations in the energy of fields that occur because perfect stillness is forbidden. The vacuum is calm, but it's not frozen. In quantum field theory, every field has a ground state. That state carries a minimum amount of energy known as zero-point energy. Because of the uncertainty principle, the field cannot settle into a single fixed value everywhere. Instead, it fluctuates slightly around its minimum. These fluctuations are constrained in both size and duration. The smaller the region of space being considered, the larger the possible fluctuations. The longer a fluctuation lasts, the smaller its energy must be. These limits are not arbitrary, they follow directly from the structure of quantum mechanics. This is why vacuum fluctuations are often described as brief and local. They occur over extremely small distances and extremely short times. At everyday scales, they average out. Nothing accumulates. Nothing builds up. But one way this behavior is sometimes described involves transient particle-antiparticle pairs. The language of particles appearing and disappearing is common, but it must be handled carefully. What fluctuates are fields. Particles are a way of describing certain interactions when energy becomes localized enough to behave as a discrete excitation. In the vacuum, fluctuations can momentarily resemble particle pairs in calculations. These are often referred to as virtual particles. They are not particles in the everyday sense. They cannot be isolated, detected directly, or stored. They are mathematical representations of temporary field excitations within interactions. The key point is not that particles pop into existence from nothing. The key point is that fields fluctuate within strict limits. And those fluctuations can influence measurable processes. Duration matters here. These fluctuations exist for extraordinarily brief intervals. They do not persist long enough to be observed as independent objects. They appear only as intermediate effects in interactions. Their influence is subtle and indirect. Scale matters just as much. Vacuum fluctuations are most significant at very small distances. As regions grow larger, the effects smooth out. At human scales, the vacuum appears quiet. At atomic and subatomic scales, it is gently restless. This balance prevents chaos. The vacuum is not unstable. It does not collapse or explode. The fluctuations are self-regulating. They are allowed precisely because they are constrained. It is tempting to imagine nothingness as a blank slate where anything might happen. Quantum mechanics does not permit this. The vacuum follows rules, energy is conserved overall, fluctuations are bounded, cause and effect remain intact. This constraint is essential. Without it, the universe would be unrecognizable. The fact that vacuum fluctuations are limited is what allows matter to exist in stable forms. Atoms do not dissolve, space does not tear itself apart. The effects of these fluctuations can be inferred through their influence on the measurable quantities. They shift energy levels in atoms. They modify the strength of forces over very short distances. They alter the behavior of particles in subtle but predictable ways. One example involves the energy levels of electrons in atoms. Precise measurements reveal small shifts that cannot be explained without accounting for vacuum fluctuations. The background activity of fields slightly alters how particles interact, even when nothing seems to be happening. Another example appears in force calculations. At very small separations, the vacuum contributes corrections to the forces between charged particles. These corrections are tiny, but they are consistent and measurable. What matters is not the size of a single fluctuation, but their collective influence over time and across many interactions. The vacuum leaves a trace. This reinforces an important idea. Nothingness is not chaotic. It is constrained activity at the lowest possible level. The vacuum does not choose randomly what to do. It follows statistical patterns defined by the underlying theory. There is a calm regularity to this. The vacuum fluctuates the way a tightly stretched surface vibrates. Small, rapid motions that never grow out of control. The system remains stable because the rules enforce balance. It is also important to note what vacuum fluctuations are not. They are not a source of free energy. They cannot be harvested. They do not violate conservation laws. Attempts to imagine extracting usable energy from the vacuum misunderstand the nature of these effects. The vacuum does not give energy away. It responds to boundaries, constraints, and interactions. When conditions change, the vacuum adjusts. That adjustment can produce observable effects, but always within the limits imposed by physics. This is why experimental confirmation matters. Vacuum fluctuations are not accepted because they sound intriguing. They are accepted because they produce precise, testable predictions. Before turning to experiments, and it is worth pausing on the conceptual shift that has taken the place. Emptiness has been stripped of drama. It is no longer a void where anything might happen. It is a structured state governed by rules that limit activity as much as they allow it. The vacuum is restless but disciplined, active but restrained. It does not contradict the stability of the universe, it supports it. This perspective also explains why emptiness resists simple description. It is neither a thing nor a nothing. It is a condition, a state defined by minimum energy and unavoidable fluctuation. Once this is understood, the next step becomes natural. If vacuum fluctuations influence forces and energy levels, then they should be observable under the right conditions. Not by watching particles appear, but by measuring the consequences of their absence. Our physics does not ask the vacuum to announce itself. It asks whether the world behaves differently because the vacuum is there. The answer quietly and consistently is yes. The task now is to isolate those differences, to shape emptiness in ways that reveal its structure, to move from implication to demonstration. Vacuum fluctuations prepare the ground for this transition. They explain why effects exist. Experiments reveal that they do. The calm hum of nothing is not imagined. It leaves marks, and once those marks are measured, emptiness becomes not just a theoretical necessity, but an experimental reality. At some point, theory must touch the world. Ideas about emptiness can be elegant, consistent, and mathematically necessary. But physics ultimately asks a simple question. Does any of this do something that can be measured? One of the clearest answers to that question comes from an effect that is surprisingly quiet, remarkably precise, and almost impossible to dismiss. It is known as the Casimir effect. In the late 1940s, the Dutch physicist Hendrik Casimir was studying quantum fields in confined spaces. Casimir was not looking for a philosophical statement about nothingness. He was working on practical problems related to electromagnetic forces. What emerged from that work, however, was a direct prediction about how empty space itself should behave. The setup is conceptually simple. Take two flat, uncharged metal plates. Place them extremely close together, separated by a tiny gap. Remove as much air as possible so that the space between them is effectively a vacuum, according to classical physics. Nothing interesting should happen. No charge, no force, just two neutral objects sitting quietly in empty space. Quantum physics predicts something else. The electromagnetic field exists everywhere, including inside that gap. Even in its lowest energy state, the field fluctuates. But those fluctuations are not arbitrary. They depend on the boundaries of the space they occupy. Only certain field modes, specific wavelengths and frequencies are allowed to exist between the plates, while others are excluded. Outside the plates, the field has more freedom, more modes are allowed. The vacuum energy outside the plates is therefore slightly higher than the vacuum energy inside the gap. This imbalance produces a force. The plates are pushed together, not because something is pulling them, but because empty space on one side behaves differently from empty space on the other. The force is small, but it is real. At separations of a few hundred nanometers, it becomes measurable with sensitive instruments. This is the Casimir effect, a force arising purely from the structure of the quantum vacuum. What makes this effect so important is not its size. It is not dramatic. It will not move furniture or bend steel beams. What matters is its origin. No particles are exchanged. No charges interact. The force emerges solely from how quantum fields behave in confined empty space. Geometry is the key. Change the shape, distance, and/or orientation of the boundaries and the force changes predictably. The vacuum responds to structure. This immediately elevates emptiness from abstraction to physical participant. Empty space is no longer just a background condition. It has mechanical consequences. It pushes. The Casimir effect has been confirmed repeatedly in laboratory experiments using different materials, geometries, and techniques. Measurements agree with theoretical predictions to high precision. This is not a one-off curiosity. It is a robust phenomenon. There is something quietly decisive about this. Vacuum energy is no longer inferred indirectly through atomic shifts or theoretical necessity. It produces a force that can be measured between macroscopic objects. Empty space exerts pressure. This matters because it removes a lingering escape route. And one could previously argue that vacuum fluctuations were mathematical artifacts, bookkeeping tools with no independent reality. The Casimir effect closes that door. The vacuum does work. It is also important to be clear about what this does and does not mean. The Casimir effect does not imply that the vacuum is unstable or explosive. The force is conservative. It does not generate energy from nothing. It depends entirely on configuration. Change the boundaries, and the effect adjusts accordingly. The vacuum is not a reservoir waiting to be tapped. It is a responsive system. There is a gentle elegance here. Emptiness does not shout to be noticed. It responds when constrained. It reveals itself when shaped. Two plates placed close together are enough to expose structure that would otherwise remain invisible. As this reinforces a pattern that has appeared again and again, space behaves differently when geometry changes. Curvature alters motion. Boundaries alter fields. Structure matters. The Casimir effect also provides a bridge between scales. It is observed in the laboratory under controlled conditions using equipment built for precision. But the principles behind it do not belong only to the lab. They apply wherever quantum fields exist, which is everywhere. If geometry can alter vacuum behavior between metal plates, it can also alter vacuum behavior near stars, inside cavities, or across cosmological distances. The same rules apply. only the scale changes. This is where emptiness begins to stretch beyond the experimental table. The vacuum is sensitive to shape and boundary. The universe is full of shape and boundary. Galaxies carve regions of space, horizons form, expansion stretches geometry itself. The Casimir effect does not explain these larger phenomena directly, but it establishes something essential. Vacuum energy is not speculative. It is not philosophical. It produces measurable forces. That fact alone changes the conversation. Empty space can no longer be described as nothing that happens to sit between objects. It reacts, it repends, it exerts influence when conditions demand it. There is also a subtle lesson about how physics advances. The Casimir effect was not discovered by looking for drama. It emerged from careful attention to constraints, symmetry, and consistency. The vacuum revealed itself not through spectacle but through precision. In a sense, this is exactly how emptiness prefers to be known. By now, emptiness has acquired many roles. It carries geometry, it hosts fields, it stores energy, it fluctuates, and now it pushes. The laboratory confirmation of vacuum energy anchors decades of theoretical work in something tangible. It shows that the quiet restlessness of the quantum vacuum is not an abstract hum. It leaves fingerprints that instruments can detect. Once that is accepted, the question naturally expands. If vacuum energy exists here between metal plates, then it exists everywhere. Not necessarily in the same form, not necessarily with the same effect, but as a property of space itself. The lab has shown that emptiness is active. The universe is much larger than any laboratory. And if empty space matters here, it may matter on the largest scales of all. By this stage, the idea of vacuum energy has become unavoidable, and it is no longer a poetic phrase or a speculative suggestion. In modern physics, vacuum energy has a specific meaning. It refers to the energy associated with the lowest possible state of quantum fields, even when no particles are present. In quantum field theory, every field contributes to the vacuum. Each field has a modes of vibration, and each mode carries a minimum amount of energy. Add together all of these contributions across all fields and across all allowed modes, and the result is a non-zero energy associated with empty space itself. This is vacuum energy. It is important to be precise about what this does not mean. Vacuum energy is not energy stored in particles waiting to be released. It is not fuel. It is not something that can be extracted at will. It is a baseline property of the fields that make up physical reality. At small scales, vacuum energy reveals itself through effects like the Casimir force and subtle shifts in atomic behavior. At these scales, theory and observation align well. The calculations are difficult, but they work. The difficulty arises when vacuum energy is considered at the largest possible scale. According to general relativity, energy has gravitational consequences. Energy affects the curvature of spacetime. This applies not only to matter and radiation, but to any form of energy, including vacuum energy. If empty space carries energy, then that energy should influence the expansion of the universe. When physicists attempt to calculate the vacuum energy density using quantum field theory, they arrive at an answer that is extraordinarily large. Even conservative estimates produce a value that, if taken at face value, would cause spacetime to curve violently. The universe would either collapse instantly or expand so rapidly that galaxies could never form. Yet this is not what is observed. Observations of the universe show that cosmic expansion is gentle on large scales. Galaxies form. Stars persist for billions of years. Space does not tear itself apart. Whatever vacuum energy exists, its gravitational effect is vastly smaller than naive quantum calculations suggest. This mismatch is known as the vacuum energy problem, sometimes called the cosmological constant problem. It is not a minor discrepancy. It is one of the largest known disagreements between theory and observation in all of physics. The problem can be stated simply. Quantum field theory predicts an enormous vacuum energy. Cosmological observations indicate a very small one. Both frameworks are exceptionally successful in their respective domains, yet when they are combined, they clash. It is tempting to rush toward explanation, to suggest hidden cancellations, new particles, unknown symmetries, or exotic mechanisms, but restraint is important here. At present, there is no accepted solution. Physicists have explored many possibilities. Some approaches suggest that vacuum energy contributions cancel almost perfectly through mechanisms not yet fully understood. Others propose that only differences in vacuum energy matter gravitationally, not absolute values. Still others investigate whether gravity itself responds differently to vacuum energy than to other forms of energy. None of these ideas has yet achieved consensus. What matters for the present discussion is not how the problem will be solved, but what the problem implies. It implies that vacuum energy is real enough to demand explanation, yet subtle enough to evade straightforward interpretation. This tension tells us something important about emptiness. Empty space is not a blank slate where theory and observation naturally agree. It is a regime where the deepest principles of physics intersect and where those principles are not yet fully reconciled. There is also a lesson in scale. At laboratory distances, vacuum energy behaves exactly as quantum field theory predicts. At cosmological distances, its role becomes enigmatic. The same concept behaves differently depending on context. This does not mean one scale is wrong and the other is right. Well, it means understanding emptiness requires frameworks that span an enormous range of sizes, from subatomic distances to the size of the observable universe. The vacuum energy problem is often described as embarrassing. But that word hides something more constructive. It highlights where understanding is incomplete. It marks the boundary between what is known and what is not. Importantly, the problem is not a failure of measurement. Astronomical observations are consistent and precise. Nor is it a failure of quantum mechanics at small scales. That framework continues to produce correct predictions. The difficulty lies in combining them. This reinforces a theme that has been developing throughout this discussion. Emptiness is not simple. It is not a leftover after everything else is removed. And it is an active participant governed by rules that interact in subtle ways. Vacuum energy, as a concept, sits at the intersection of those rules. It links quantum fields to space-time curvature. It connects the smallest fluctuations to the largest structures. At present, physics does not yet know how to make all of these pieces fit together seamlessly. That uncertainty is not a flaw to be hidden. It is a fact to be acknowledged. There is also something calming about this admission. Nature is not required to be simple at every level. Understanding unfolds gradually. Some questions remain open not because they are unanswerable, but because they are being asked at the edge of what current theories can handle. Vacuum energy, defined carefully and observed indirectly, is one of those edge concepts. It is real enough to matter, yet elusive enough to resist final explanation. This unresolved tension does not undermine the reality of vacuum energy. It deepens it. It shows that emptiness is woven into the structure of the universe in ways that are not yet fully transparent. As attention shifts outward from laboratories to galaxies and beyond, the question becomes unavoidable. If vacuum energy exists everywhere, however small its effect may be locally, what role does it play in shaping the universe as a whole? That question belongs to cosmology, and it is there, on the largest scales imaginable, that emptiness takes on one more unexpected role. Once emptiness is allowed to carry energy, structure, and rules, the behavior of the universe at the largest scales begins to make more sense. Space itself is no longer a static container, and it becomes something that can change, and one of the most important ways it changes is by expanding. Cosmic expansion is often misunderstood as objects moving through space like fragments flying away from an explosion. That image is familiar, but it is misleading. The expansion of the universe is not primarily about galaxies racing through a fixed void. It is about space itself stretching. Distances increase not because galaxies are actively traveling outward, but because the space between them grows. Two galaxies can remain nearly at rest relative to their local surroundings and still drift farther apart over time. The separation grows because the metric that defines distance is changing. This idea was not obvious when it was first discovered. In the early 20th century, astronomers were still debating whether distant nebulae were part of the Milky Way or separate galaxies entirely. Observations were limited, distances were uncertain. That changed through the work of Edwin Hubble. Using observations made at Mount Wilson Observatory in California, Hubble studied the light from distant galaxies and compared their apparent brightness with known stellar properties. He was able to estimate their distances and compare those distances to how their light was shifted toward longer wavelengths. What he found was remarkably simple. The farther away a galaxy was, the more its light was shifted. This shift indicated that distant galaxies were receding faster than nearby ones. The relationship was systematic and proportional. This was not random motion. It was a pattern. The conclusion was unavoidable, on large scales, that the universe is expanding. What matters here is how that expansion is interpreted. The galaxies are not fleeing from a central point. There is no center to the expansion. Every region sees distant galaxies moving away regardless of location. This is exactly what is expected if space itself is stretching uniformly. This stretching happens everywhere, including regions that appear empty. In fact, it happens most clearly in emptiness. Dense structures like galaxies and clusters are held together by gravity and internal forces. They resist expansion. The vast, sparsely populated regions between them do not. Cosmic voids, enormous regions containing very little matter, expand along with space itself. There is nothing in these regions pushing outward. There is simply nothing resisting the stretching. This is a crucial shift in perspective. Expansion does not require matter to move or act. It requires space to evolve. Even a region stripped of particles will grow in size as the universe expands. This behavior follows directly from general relativity. The equations governing spacetime allow the geometry of space to change over time. Solutions to these equations describe expanding or contracting universes depending on the balance of energy and curvature. What Hubble observed was not the cause of expansion, but its effect. The expansion was already encoded in the structure of spacetime. Galaxies merely revealed it by drifting apart. Scale matters enormously here. On small scales, expansion is negligible. The distance between atoms in a table does not grow. The solar system does not expand. Even galaxies remain bound. Local forces dominate. On larger scales, her gravity still shapes structure, but it does not prevent expansion entirely. Galaxy clusters form and persist, yet clusters themselves drift apart over time. Beyond that, on the larger scales of all, expansion dominates. This scale dependence is why expansion can coexist with stability. The universe can expand while still allowing stars, planets, and people to exist. Expansion is not a tearing force. It is a gradual stretching that becomes significant only over immense distances. It is also why emptiness plays such a central role. Most of the volume of the universe is not filled with matter. It is filled with vast regions of low density. These regions faithfully track the expansion of space itself. In that sense, emptiness reveals the universe's behavior more honestly than matter does. Matter resists, distorts, and complicates, and empty space stretches freely. This does not mean that expansion originates from emptiness alone. The rate of expansion depends on the total energy content of the universe, including matter, radiation, and whatever else contributes to spacetime curvature. But emptiness provides the stage on which expansion becomes visible. There is a gentle conceptual shift here. Instead of imagining expansion as something happening to objects, it becomes something happening to space. Distance itself evolves. This idea can feel abstract, but it has direct observational consequences. Light traveling through expanding space is stretched along with it. Its wavelength increases. This is why distant galaxies appear redshifted. The light has not lost energy through friction or resistance. The space it travelled through has changed. And even the most empty regions participate. A photon crossing a cosmic void experiences the same stretching as one crossing a region filled with matter. Emptiness does not shield space from its own evolution. By now, empty space has accumulated a remarkable list of responsibilities. It carries geometry, it hosts fields, it stores energy, it fluctuates, it pushes between plates, and it stretches slowly and steadily on the largest scales imaginable. What remains is a final and surprising twist. For much of the 20th century, scientists expected expansion to slow over time. Gravity, they reasoned, should gradually pull everything back together. Observations would soon reveal otherwise. The expansion of the universe is not merely continuing, it is speeding up. And that discovery will force emptiness to take on one more role, one that reshapes the future of the cosmos itself. For much of the 20th century, there was a quiet expectation guiding cosmology. The universe was expanding, but gravity should be slowing it down. Matter attracts matter. Over time, that attraction ought to act like a brake, gradually reducing the rate of expansion. Whether the universe would eventually collapse, coast forever, or settle into some balance remained open. but deceleration felt natural. That expectation was reasonable. It followed directly from general relativity and from the known behavior of matter and an energy. Expansion required explanation, but slowing expansion felt inevitable. Then observations began to say otherwise. In the late 1990s, 2 independent research efforts set out to measure the expansion history of the universe with greater precision than ever before. These efforts were known as the Supernova Cosmology Project and the High Z Supernova Search Team. Their focus was on a particular kind of stellar explosion called a Type 1, a supernova. Type 1 supernovae are valuable because they behave in a remarkably consistent way. When a white dwarf star reaches a critical mass and explodes, the brightness of the explosion follows a predictable pattern. This makes such supernovae reliable cosmic distance markers. By comparing how bright they appear with how bright they're known to be, astronomers can determine how far away they are. These teams observed supernovae in distant galaxies, looking back billions of years into cosmic history. They measured both distance and redshift, allowing them to reconstruct how fast the universe was expanding at different times. The expectation was clear. Distant supernovae should appear brighter than they would in a steadily expanding universe, reflecting a past when expansion was faster and had since slowed. They did not. Instead, the supernovae appeared dimmer than expected. The implication was startling. The expansion of the universe had not been slowing down. It had been speeding up. This was not a subtle effect buried in noise. It was consistent across observations. 2 independent teams using different methods and analyses arrived at the same conclusion. The universe's expansion is accelerating. This discovery reshaped the cosmology almost overnight. An accelerating expansion requires something that counteracts gravity on the larger scales, something that does not clump like matter, something that exerts a kind of repulsive influence as space expands. This something became known as dark energy. The name is intentionally modest. Dark energy does not imply a specific substance or mechanism. It is a label for a set of observed effects. It describes whatever is causing the observed acceleration. What makes dark energy especially relevant to emptiness is where it appears to reside. Observations indicate that dark energy is not concentrated in galaxies or clusters. It does not pull in dense regions. Instead, its influence seems uniform across space. It behaves as a property of space itself. As the universe expands, the total amount of dark energy increases. And not because more is being created, but because there is more space for it to inhabit. The energy density remains roughly constant even as space grows. This is profoundly counterintuitive. Matter becomes more dilute as space expands. Radiation thins out, but dark energy does not fade. It persists. This persistence suggests that dark energy is tied to the vacuum of space, to emptiness itself. It is important to emphasize what is known here and what is not. The accelerating expansion is observed. The influence of dark energy is inferred from multiple independent measurements, including supernovae, cosmic microwave background observations, and large-scale structure surveys. These observations are consistent. What dark energy is remains uncertain. There are theoretical interpretations. And one possibility is that dark energy corresponds to a cosmological constant, a term originally introduced by Albert Einstein into his equations of general relativity. In this view, empty space has an intrinsic energy density that causes it to expand. Another possibility involves dynamic fields that change slowly over time. Other ideas explore modifications of gravity on cosmic scales. None of these explanations has been confirmed. What matters is that explanation has not outrun observation. The data come first. The universe is accelerating. Any acceptable theory must account for that fact. This discipline is essential. It keeps speculation grounded. Dark energy is not a placeholder for imagination. It is a response to measurement. The role of emptiness in this picture is striking. The vast majority of the universe's volume is empty space. Galaxies and clusters occupy only a tiny fraction. If dark energy is a property of space itself, then emptiness dominates the universe's behavior. On the largest scales, matter becomes secondary. It shapes structure locally, but it does not control the overall expansion. Empty space does. This reverses a long-held intuition. Historically, emptiness was treated as absence, as what remained when everything else was removed. In the modern cosmological picture, emptiness becomes the main actor. This does not mean matter is unimportant. Stars still shine, galaxies still form, chemistry still operates, but the long-term fate of the universe is governed by how space itself behaves. There is a calm audacity to this conclusion. Without drama or spectacle, that empty space quietly takes control of cosmic evolution. The acceleration is gentle. It does not tear galaxies apart. It does not disrupt bound systems. It becomes noticeable only across immense distances and over billions of years. The universe does not explode outward. It stretches faster and faster, patiently. This gentleness is important. Dark energy does not behave like a violent force. It does not push objects apart locally. It changes the rate at which space expands globally. That distinction preserves the stability of the universe while reshaping its future. It also deepens the connection between emptiness and energy. The same vacuum that produces subtle forces between metal plates now appears to shape the expansion of the cosmos. The same concept spans laboratory experiments and astronomical observations. But this does not mean the two are identical in mechanism. Caution is required, but the conceptual link is unavoidable. Energy associated with empty space has consequences at every scale. There is a temptation to treat dark energy as mysterious in a dramatic sense. In practice, its mystery is quiet. It reveals itself through careful measurement, patient analysis, and consistent patterns. The acceleration of the universe was not discovered by looking for something strange. It was discovered by noticing that something expected did not happen. That absence of deceleration mattered. Once again, emptiness reveals itself not by shouting, but by refusing to behave as expected. At this stage, emptiness is no longer a background assumption. It is the dominant component of the universe's energy budget. It shapes the past, the present, and the future of cosmic expansion. The universe is not being driven apart by the matter flinging itself outward. It is being carried along by the properties of space itself. Empty space, once thought to be nothing at all, now appears to be the quiet engine of cosmic history. And that realization forces one final reassessment. If emptiness dominates the universe's behavior, then understanding emptiness is not a side question. It is the central one.